Well, now that we know all about the ionic structure of the different atoms and the way in which they can form different chemical bonds, we're going to talk in this chapter about chemical reactions. In other words, how to make and break those chemical bonds. The idea here is that the chemical symbols, the formulas, the equations can be used concisely to represent elements, compounds, and what happens in a chemical reaction. So all that knowledge that you have from the prior two chapters, you're going to now be applying. So there's several types of chemical formulas that we have. We have the empirical formulas we talked about. This identifies the elements and presents in terms of identifies elements that are present in terms of the simplest whole number ratios. Sodium chloride, NaCl, H2O. And then there's also molecular formulas. This identifies the actual number of atoms in a molecular compound. Again, water is the same example, but not this one right here. This is an ionic compound. It's not per se a molecule. So we also learned that there's ways to represent these as structural formulas, and you'll have more about that in a lab today. Water, for example, can be either represented by the name, by this representation of the elements and how many are present in that molecule. This one right here that shows the approximate space that the electron structures fill. And this one right here that shows the structure of the bonds involved in each one. And you can see that we have the same thing for ammonia, hydrogen peroxide, and carbon dioxide with the different bond structures here. And so there's, when we talk about chemical equations, we're going to be using these right here. When we talk about how those reactions can take place, we have to sometimes look at it in terms of the structural formula, in terms of what bonds or electrons are available to make or break bonds. So, empirical or molecular formula. Empirical, we use those when it's ionic. In other words, it lacks discrete units, composed of both metallic and non-metallic elements, and it has an electronegativity of greater than 1.7. We learned about that in the last chapter, right? Molecular ones are those that are covalent compounds, usually nonmetals bound to nonmetals. Molecular and empirical formulas can be present. You can have glucose, which is the molecular formula is C6H12O6, but these all have the common denominator of 6, so the empirical formula for this molecular formula would be CH2O. Each one divided by 6. We also have molecular weights and formula weights, and these are an important aspect of what we have to calculate, and you did some of those calculations during the last chapter. The formula weight is the sum of the atomic weights of all the atoms in a chemical formula. So, for example, what's the molecular weight of a table sugar sucrose that is C12H22O11. Well, there's 12 carbon atoms, so that's 12 times 12 is 144. 22 times 1 is 22. 11 times 16 gives you a total for all of those of 342 for the formula weight or molecular weight of sucrose. We also need to look at things in terms of percent composition. Sodium fluoride is added to water supplies. It's written as NaF. So to determine the formula weight, it would be 42.0, 23 from sodium, 19 from fluorine. So what is the percent of each one? Well, if you have, you can probably see this easier on your download than you can on this particular one. For sodium is 23 units here, divided by the 42 for the total molecular weight. So that times 100% gives you that the percent of this that is sodium is 54.7%. Doing the same thing for fluorine, you have 19 in the numerator here. You've got one of them. That's where the one came from here as well. And then you have 42 in the denominator, because that's the total weight. So it's the part divided by the total times 100% gives you that this formula weight is 45.2% fluorine. So because of rounding, sometimes these do not add up to exactly 100%. You can see it's off by a 0.1 in this particular case. In chemical reactions, these occur through the formation and the breaking of chemical bonds between atoms. Changes in matter, creation of new material, energy exchange, all are involved in these chemical reactions. A chemical equation is a concise representation of that chemical reaction. Here they have the really great looking one of the chemical reaction of the carbonization of some protein. Actually, looks pretty good there. So writing chemical equations, to illustrate the fundamental aspects, the following things need to be noted. The substances undergoing the reaction are called the reactants, and these are placed on the left side of the equation over here. Then there's going to be a little arrow, and then the substances generated by the reaction are called products, and their formulas are going to be over here on the right-hand side. Plus signs separate individual reactants, so if you have more than one reactant, you'll have the different molecules separated by a plus sign. You have the arrow sign in between, as I mentioned, and then if you have more than one product, you will have plus signs between the different ones there. The relative numbers of reactants and product species are represented by coefficients. These are the numbers placed immediately to the left of each of the formulas that we have talked about here. Now, if the coefficient is 1, usually you don't write that one down. So the coefficients is to use the smallest whole number in the chemical reaction. These coefficients represent the relative numbers of reactants and products, and therefore they may be correctly interpreted as ratios. In the previous example, we had methane and oxygen, right? Methane was being burned, okay, to yield carbon dioxide and water. So you had one here, CH4. You had two O2 molecules reacted to form CO2 over here, and then H2O over here. So you had one molecule of methane, two molecules of oxygen. These were your reactants. Your products were one molecule of carbon dioxide and two molecules of water. So, again, just to reiterate, reactants are the substances before the reaction, products afterwards. Products word representations are not sufficiently precise. Chemical symbols and formulas are needed for quantitative purposes. And so you have CO2 plus C, carbon plus oxygen forming carbon dioxide, right? You could also react carbon with oxygen to form CO, carbon monoxide, right? That usually happens when you don't have a whole lot of oxygen present. But for that reaction to be balanced, you'd have to put a 2 in front of this, and then you'd have 2C plus O2 becomes 2CO. And that's what is shown on the bottom of the slide if you downloaded this material. So balancing equations. The first law, way back when we first started talking about chemistry, is the law of conservation of mass. Atoms are neither created nor destroyed in a chemical reaction. So if you've got two mercury molecules here and two oxygen molecules on this side of the equation you have to have two mercury atoms, and you have to have two oxygen atoms. This is in the oxygen, this is the gaseous form of it, and this is just the solid form here. Now, You can change the coefficient in front of the chemical formulas, but not the subscripts within the formula. So this 2 does not change. In order to balance this equation, you have to put a 2 in front of this right here and a 2 here if you had not had those before, but you do not have to add anything to this one, and you do not change subscripts. A chemical equation described previously is balanced. In other words, there's equal numbers of atoms for each element represented on the reactant side and on the product side. The number of atoms for a given element is calculated by multiplying the coefficient of any formula containing that element by the element subscript. For example, if an element appears in more than one formula on a given side, the number of atoms represented in each side must be computed and added together. For example, both product species in the example reaction carbon dioxide and water contain the element oxygen. So one carbon dioxide molecule has 2 oxygen atoms per carbon dioxide molecule. Plus, you have 2 oxygen molecules in the one oxygen atom per water molecule, and you've got 2 water molecules. So 2 times 1 plus 1 times 2 gives you a total of 4 oxygen atoms. See how simple that is? So balancing this equation, right here you have 1 in front of the methane. So you've got 1 on this side of the equation, right? You've got 1 on this side of the equation. So you got 1 times 1 is 1. 1 times 1 is 1 here. So 1 equals 1. Yes, they're balanced. Here you have 4 hydrogen on this side. Here you have 2 times 4, 2 times 2, which is 4 on this side. So 1 times 4 here, 2 times 2 here for 4. So 4 equals 4. So yes, it's balanced. Here you have 2 times 2 to give you 4 oxygen atoms on this side of the equation. 2 times 1, 2 times 1 gives you 4 on the product side. So this is balanced. 4 equals 4. Now in this one right here, this is not balanced. Here you have 2 hydrogens here, but you have 1 oxygen here, and 2 here. So it's not balanced. What you would need to do is you need to put a 2 in front of this one right here, wouldn't you? If you had a 2 here, it still would not be balanced because you would have 4 here and you'd only have 2 here. So you have to put a 2 in front of this one as well. If you had a 2 here and a 2 here and just leave this as a 1, then you finally have a balanced equation. So to achieve balance, the coefficients of the equation must be changed as needed. And as I said, subscripts identify the identity of a substance, so you cannot change them without altering the quantitative meaning of the equation. C, for example, means 1 carbon atom. O means 1 atom of oxygen. O2 means you have 1 molecule of oxygen consisting of 2 atoms of oxygen. CO means you have 1 molecule of carbon monoxide consisting of 1 molecule of carbon attached to 1 molecule of oxygen. CO2 is 1 carbon atom, 2 molecules of oxygen. 3CO2 means you've got 3 of the ones that you just described above. Each one of them has 1 carbon atom. Each of them has 2 oxygen atoms. So the hydrogen, we already balanced that equation right there. And I think we will end this particular section and then go on to the next unit.